Hello everyone. In this third video of TensorFlow, I'm with you with the major functions that you need to know in TensorFlow for arithmetic and linear algebra. So if you want to add or subtract two numbers, there are the commands tf.math.add and .subtract. So you have to go to the library of math under tf TensorFlow to add and subtract, but you can simply add and subtract too, right? So you might say, well, if I have one constant 3 and if I have one constant 2, two tensors, can I simply add them together, right? So something like this. And so let me show you. So you define y like that is tf constant 3, and another one x is tf constant 2, and you want to add them together. You can say what? You can say print, and then you say what? You say tf.math.add of x and y, right? So you can simply add them together, right? Let me here add a simple code for that part and get rid of that in this portion. So if I run that, you see here it says 5. Now, if I simply say, what about 2 plus 3? Right? X is simply constant math of 2 plus 3. Can I do that? So can I add 2 and 3 and then what? And then convert it to a constant? Would that work? You see, it does. Okay, so this 2 plus 3 is actually working, and it is a tensor, right? So you can do it that way if you want. So we have the addition and subtraction, but more important functions. Absolute value is under math.abs, so that's the absolute value. If you want sine function, which gives -1 for negative numbers, 0 for 0, and 1, +1 for positive numbers, you can use the math.sine function. And for ceiling, floor, and rounding, we have the ceil, floor, and round functions, right? So if I run this portion for you, you see here that the absolute value of -1 is equal to 1, right? That's the answer. The sine of -5 is -1. The ceiling of 1.2 is 2. The floor of that is 1. And the round of that is also 1. If you want exponential functions, you have to use .axp. If you want natural logarithm, you have to use .log. So just like MATLAB, .log here is natural log. It's not log 10. And you can see that here, right? So this is exponential of 1, which is the Euler number, right? 2.718. And you see here, the natural log of 10 is 2 point something. If it was log 10, that would be 1, but you see it's not. By the way, one very important thing is the exponential function and the logarithm function. You need to pass to them a number with decimals. They have to have floating numbers. They cannot be integers. So if you pass number 10 to it like this, you are going to get some error. You see here? So you cannot do that. You might say, really, for exponential, do I also need that? Well, let's try it. You see, you do. So exponential and log, they both need that. So now you might say, what if I want log 10 of 10? Well, then you need to divide what? You need to divide the math log of 10 by what? You have to use the logarithm formula, right? So log of a in the base of b is what? Right, it's natural log of a divided by natural log of b. So let's say if I want 100 and I want log 10 of that, what should I do? So if I just say natural log of 100, of course, it is what number? Let's take a look. So it is, I forgot to change this number here. Okay, so that number is 4.6. But again, if you want like 10, as I said, you have to divide. So you can do something like this. Say log of 100 in the base of 10 is what? You have to use division. Okay, so you have to divide this number by natural log of 10, natural log of 100 by 10. Would you get it? Well, let's find out. So we run, you see no error. Now we go and you see the number is what? 2. So we don't have a log10 function, but we can use the logarithm formula. Okay, let's move on. So what about square root? Do we have a function for that? Yes, that's a square root. Important thing, again, it needs a floating number. Can I do a power? Yes. For power, I don't need the numbers necessarily to be floating. They can be integer. So I want to raise 2 to the power 5. I use the math.pow, pow, 2 to the 5. And if you run it, you see here, I have what? 32. And the square root of 9 is what? Is 3. Okay, so they're working. What about trigonometry function? So here, you see, if I want to use sine, there is sine function, cosine function, tangent function, and so on. And the problem is they all accept the numbers in radians. And we don't have a function like sine d or cosine d that we had in MATLAB that they accepted a number in degrees. So you have to pass the numbers to them in radians, right? Here, look, when I said what is sine of 30, is 30 radians, not 30 degrees. Look at the number. You see, it's not half. It's negative 0.98. So if I want, I have to convert that 30 into radians. How do I do that? I need to multiply it by pi divided by 180. And for pi, I can use the numpy pi, right? I can use numpy.pi. And that, now you can see it's exactly what? 1/2. So pay attention to that. The other thing is, they also, these trig functions, they require numbers with floats. Okay, they need decimals. You cannot just say 30. You have to use .0. And the same thing with arc functions, arc sine, arc cosine. You have a10, a sine, and the number they return is in radians, and the number you pass to them is with decimals. So what is arctangent of 1? You see the answer is what? Pi over 4, which is exactly 3.14 divided by 4.785. Okay, so what about modulus? Well, use the dot mod, 7 and 2. The result should be 1, and it is, as you can see. Do we have anything for complex numbers? Yes, everything we had in MATLAB or Python, we have it here. So here I define a constant, a complex number. And as I told you, if you want to define complex numbers, you use J, you cannot use I. And there is no need for any asterisk or anything. You just say 2 plus 3J. Right? And you can show it. If you want conjugate of that, you can use math.conj. If you want the angle of that or argument, use .angle. .abs is the magnitude. .image is the imaginary part. .real is the real part. So you have all of these functions here. I'm only showing you the complex conjugate of 2 plus 3j is what? 2 minus 3j. So these are some basic what? These are some basic arithmetic functions. Now, if we move on, what about simple logical commands? Well, we have some logical commands, so I need to maybe add something here. And for instance, you can compare an array against another array or an array against a constant. So here I'm comparing an array of 2 and 4 against a constant 3, or if you want, you can add one more number here. So I'm comparing array of 2, 3, and 5, or maybe let's add a 3 as well here, against number 3, and I have the command math.equal. So I check each and every one of those numbers against 3, and so this should give you a logical array. Or if it's not equal, I say not equal. If it's greater, I say greater. If it's greater than or equal, you say greater underscore equal, right? You see it here. Or you say less, and you say less underscore equal. Okay, so you can use all of those. Let me run that for you. So you see here, is y equal to x? Well, 3 is not equal to 2, not equal to 4. So you get 2 falses, but equal to the last number, so you get a true. You see the shape of it is 3 by nothing, which means it's an array. and D type is what? Boolean. Okay, now not equal to, of course, you get 2 trues and a false. Then greater, only 4 is greater than 3, so you get only 1 true. Less than or equal, you get 2 trues for 2 and 3. And then here, if we move on, I define another vector z. And if you want to have infinity or nan inside an array, you can do that. Just pay attention that TensorFlow does not have inf. So you cannot say tf.inf or tf.nan. These don't exist. If you want to bring them in, you have to use the numpy. So here, my first element is infinity, second one is nan, third one is 5. I want to see if any of them is an infinity or any of them is a nan, so I use the isNan or isInf command. And you see here, it says what? Of course, for z, the first element is an infinity, and the second element is what? A nan. And there are other commands like and, or, not, right? And XOR. So we have math.logical underscore and underscore or underscore not underscore XOR, exclusive or. And here I define 2 constants. One is true, so X and Y are Boolean in this, and Y is false, and then I use a logical and here, and of course and of true and false is false. So as I said, there are other commands that you can use. By the way, before I go to linear algebra, just out of curiosity, so in this case, if I had X and Y both vectors, what's going to happen when I use the command equal or something, right? So if I go ahead and define something like this, okay, so my vector Y is what? 3 and 4 and -1. When I run this portion and say is X and Y equal, what would you get? Would you get anything? Well, look. It says false, true, false. So what happened? It compared element to element. You see, if it was 1, it compared all of the elements of the vector against the scalar. But now that they are both vector, it's comparing element to element. 2 not equal to 3, so that's false. 4 equals 4, that's true. 3 not equal to -1, that's false. Or when I say not equal, it's the opposite of that, of course. If I say greater, what's going to happen? It compares each element in X if it's bigger than the corresponding element in Y. So you see only the last element is bigger than the corresponding in Y. So that's why the result is false, false, what? True. So I just added it for you here so you can see that basically. And now that we have this part, let's go to linear algebra. So here I define a matrix A, and I show it, and another matrix B, and I show it. How can I multiply 2 matrices? I use the command tf.matmul. This is the matrix multiplication. Okay, so it multiplies the 2 matrices according to the formula we have for product of matrices. If you want to do element-wise product, element to element, then you simply use the command tf_multiply. So multiply means element-wise, something that in MATLAB you had A dots star B, and regular multiplication was A asterisk B, okay? So that's matrix multiplication versus multiply. And if you want to divide, of course, you have to divide element by element, and that's what this command divide is doing, okay? So here, if I run that for you, you see, that's matrix A, this is matrix B, this is the product. You see, if I multiply first row by first column, 1 times 0, 2 times 1, you get a 2, right? Or second row, let's say, times second column, 4 times -2 plus 3 times 5, that's 15 minus 8, that's what? 7. So you see, it is real matrix product, but if I want to do element by element, so 1 times 0, that's a 0, right? 2 times -2, that's a what? That's a -4. And division, you see here, when I'm dividing 1 by 0, I get a what? I get an infinity. Okay, so these are some basic things. And if I want to transpose, I use tf.transpose. It simply will transpose the matrix for me. If I want to get determinant or inverse, I have to use the sublibrary linear algebra. So I have to say tf.linalg.determinant. And important thing about the determinant and the inverse is the numbers, the entries of your matrix or your tensor in this case, they have to be floating numbers. They have to have decimals. Otherwise, these two commands won't work. So I can use that, and that will give me determinant. I can use .inv, and that will give me what? Inverse. If I want eigenvalues, I use the command ig with an extra h. There is another version that does not have this h, and it has two outputs. The first one is the eigenvalues. The second one is the eigenvectors here. So if we go down, you can see. Remember, your matrix was 1, 2, 4, 3. So now the transpose is what? 1, 4, 2, 3. Determinant is, of course, what? 1 times 3 minus 2 times 4. So that's -5. Inverse, you know the formula for it. And here you see these two are the eigenvalues. And the eigenvectors are these two. That's first column corresponding to first one. The second column corresponding to second one. Okay? So these are important commands that you need. What else do we have? So here, what about dot and cross product of vectors? So here I define vector A, I define vector B, and to do the dot product, I use the command tensor dot. If I want the cross product, I go again to linear algebra and I use dot cross. And that should perform the dot and cross. Let's see here. So if we go down, that's A, this is B. If we do dot product, that's 20 plus 6, 26 minus 1, that's 25. And if I do cross product, of course, you should be able to get this 3 by 3 vector. Okay, then if we go forward, what about min or max or average or sum of a vector or the location of min or max? So here, if you want the min, the command is not .mat.min. It's .reduce _ min. Okay? If you use the command min, you have to pass to it two numbers, A and B, and it will tell you which one is the minimum. So if you want the minimum of an entire vector, you have to say reduce.min. If you apply to a matrix, then you have to provide the second number, which you tell it along which axis, which direction you want the minimum, along rows or along columns. So the command reduce min will give you minimum, the argmin will give you the location, and reduce _ mean or average gives you the average, reduce _ sum will give you sum of the elements. And you have reduce max, you have argmax, let me add that. You have reduce prod, which is product of the elements, reduce standard deviation, cumulative sum, and cumulative product. All of them are under what? Dot math. Okay, so math dot this and so on and so forth. Okay, these are all under math. So let me just add them for you. So here, if we go down and look, you see in this vector, the minimum is of course -9. The location, it says 4. That's true. This is location 0, 1, 2, 3, and that's location 4. What is the average? Well, you have to add everything together. That's 10, 16 minus 9. That's 7. 7 divided by, let's make sure. Yeah, that's right. That's 7 divided by 6. It gives me a 1. So it did not convert it to a float. It went with integer. You see here, it truncated it. It either rounded it or truncated it. You see? Because these elements, the way I defined them, they didn't have a decimal. So the average it gave me also didn't have any decimal. But the sum is, of course, 7. So if I want really to get accurate numbers, I better what? I better come down here and I better add a .0, add a decimal. That should give me a lot better more accurate results. So let's run it one more time. You see, now the average is 1.1/6, 1.16. Okay, so be very careful about that. And that's it. These are the basic commands for linear algebra. I know you might want, for example, singular value decomposition, Cholesky factorization, all of those, and they're all available. Okay, these are the basic commands for linear algebra, for logical commands, and for arithmetic. I'll share this file, the download link for it, under the video description. Take a look at it, and I'll see you in the next video. Thank you.